Well, now that we know how to describe lines in both 2 dimensions and 3 dimensions using our vector equations, it's actually quite simple for us to find the angle between those 2 lines. If you remember, we have each line is going to have what we call a direction vector. That's the vector which we call B in the previous lessons, right? So I could have, let's say, line 1, and I'm going to give you the parametric equations of that line, and we're gonna analyze what is the angle between those 2 lines. So let's say the first line, one of the equations is x equals 2 minus 3t, and y equals -1 plus t. Obviously t is a real number. And I've got a second line. My second line is described by x equals 1 plus 2s, so it's just a different parameter, and y equal to -4 plus 3s. Alright, so those are our 2 equations. So the first thing that we can actually remember is that we can get back to our vector form. So xy would be 2 and -1, right, plus -3 and plus 1 t. If we expand those, if we get each line, we get back to the parametric equations. So this is line 1. What about line 2? It's just the same. I mean, different values, but same logic. So 1, -4, close it, plus 2 and 3, s. So that's the point that we wanted to arrive now. If we observe those lines, well, this point is those points which are given, they are completely arbitrary, so they could be any point, right? I could have a point which is a bit more to the left, and we would change our parameter. So those points, they don't tell us much. I mean, they fix the points so we know that it's not a family of perpendicular lines, but the actual part of our equation that gives us direction is the direction vector. So just by comparing those vectors, we could find out what's the angle between them. So if I extract, let's call this B1, vector B1, and let's call this vector B2. So all we have to do to check what is the angle between those 2 lines, L1 and L2, is compare what's the angle between those 2 vectors. And that's something that's known. So if you remember your cosine rule, or just last chapter with vectors, so we could calculate the angle between 2 vectors just by doing the cross product. Sorry, the dot product. We're not gonna do cross product in this course. So B1 dot product with B2 over absolute value of B1, so magnitude of B1 and magnitude of B2. This is how we find the angle between 2 vectors, and then we can just do the inverse cosine or arc cosine. From this we can find theta to be the arc cosine of whatever's here, right? B1 dot product over absolute value, so magnitude of B1, magnitude of B2. When you have a multiplication between 2 numbers, doesn't matter if it's a dot product or not, it's just a regular multiplication because they're both scalars. Alright, so B1 dot product with B2. So how much is this? Right, this is dot product. Those are vectors. So B1 is -3 and 1, and B2 is 2, 3. So we multiply each of them and we sum them up. So negative 3 times 2, that's negative 6, plus 3 times 1. So this is negative 3. Now, absolute value, so magnitude of B1. So magnitude of B1, root, what are the coordinates of B1? Negative 3 and 1. So negative 3 squared, that's 9. 1 squared, that's 1. So that's root of 10. Our second vector here, B2, when we extract the magnitude, so that's 2 squared, that's 4, plus 3 squared, that's 9. So that's root of 13. Well, now if we work this out, then our angle, so our, let's say our cosine of theta, so let's first do this equation here. It would be, so dot product between those two would be negative 3 over root of 10 over root of 13. Now here on top there is something interesting that we can actually do. Basically, if we take the absolute value of those two, we'll always have a positive value here. And what's that's going to tell us? Well, basically we're going to neglect negative angles, and it makes sense to us. Or we're going to neglect angles which are between 180 and 360. So this means, just, well, let's say that this is line L1 and this is line L2. So this basically means that we're always going to use the angle which is the smallest one. So we're going to use the angles which are actually acute and not the obtuse ones. So for example here we could have an angle which is, well, it's basically 180 minus theta, but this would be, from the drawing, if it's up to scale, this would be obtuse, this would be acute. So we're always looking for the acute angle. So we may get the absolute value here, because this negative 3, it doesn't matter. It would give us this angle which is larger, but we don't care about it. So let's get all the absolute values. If the angle here, if those values, if they were already positive, it just meant that those vectors, the angle which you were taking into account was already the smallest one. Okay, so if we do this, that's 3 over root of 10, and then you move over root of 10 multiplied by root of 13. So you would have a cosine of theta of approximately 0.2631. Okay, and then if you extract your angle, you would have an angle of approximately, up to 3 significant figures, 74.7, which would be approximately 1.30 radians. And yeah, that's it. So this is the angle between those two lines. Now we could have an equation or equations for lines in 3 dimensions, like these ones. So we have this line 1, so it's described by this vector r1, and this is your point, your arbitrary point, this is your parameter s, and this is your direction vector. And same thing here, r2 is your vector which describes this line, this is your arbitrary point, this is your parameter t, and this is your direction vector. So let's say that the question is asking us, what's the angle between those two lines? So there is an easy way and there is a hard way. Now the easy way, if you just look at those direction vectors, they are the same. So since they are the same, couldn't I express b1 equals some constant value times b2? Yeah, well, k, it's just that k is 1, right? This is actually true, but k is 1. Doesn't matter. The whole point here is, if this is true, it means that they are parallel. So if they are parallel, we can say, well, B1 and B2, they are parallel, right? So we can draw two bars like this. This means that they are parallel. If they were perpendicular, you would basically draw a flat line and another line like this, B1, right? But they're not, so I won't put this here so you won't make you guys confused. So since B1 is parallel to B2, R1 is parallel to R2, right? And obviously L1 is parallel to L2. This is all of those, they basically mean the same thing. Now, however, the question is asking us for the angle, so the angle would be 0. So let's say theta is the angle between them is 0. Now, you don't have to trust me. You could use the equation that we have seen before, and we would have the absolute value of the dot product between the two direction vectors over the absolute, so the magnitude of the first vector and the magnitude of the second direction vector. So the product, so the dot product of them, so 3 and -3, if we multiply them, that's 9, plus 1 and 1, that's 1, and -2 and -2, that's 4, over, right, this is going to be a positive value, so I will not put the absolute brackets, the absolute sign here anymore. Now B1, what's the magnitude of B1? Since they are the same, the magnitude should be the same, but let's calculate for one of them. So let's say B1, it would be root of 3 squared. -3 squared and 3 squared is the same, so it doesn't matter. Plus 1 squared, that's 1, plus -2 squared, so that's 2 squared. I'm just putting everything positive since we're going to square them. Now 3 squared, that's 9, 1 squared, that's 1, and 2 squared, that's 4. So this is root of 4 plus 1 plus 4, which is root of 14. This is the magnitude of one of those direction vectors. If I do the same thing for the second one, since all coordinates are the same, I would expect to get the same value as well. So the magnitude of B2 is also root of 14. So I can get those values here. So I would have root of 14 times root of 14. If I work those values up here, I would have then 14 over root of 14 times root of 14, that's 14. So all of this is equal to 1. So what does it mean for cosine to be equal to 1? If you remember your unit circle, so cosine is our x. So we're looking for cosine, right? Now when is it equal to 1? Well, when we start counting, this is where we start. So here it's going to be equal to 1. And yeah, and that's it. I mean, we would have, since we're talking about absolute values, right, we have assumed that those were absolute. This angle here would also give us the same angle between them, but it's what we were talking about before. I could describe this as 180 or 0, so let's go with 0. So theta here is 0 degrees or 0 radians. So as our last example, let's say that we want to find the angle between those two lines. Now I don't have the parametric equations, right? The parametric equation for each of those lines. But let's try to analyze those lines. So let's try and get some parametric equations, or at least try and get the direction vector, because that's actually what's important to us. Everything else is, for example, the points that we choose, it's arbitrary, so the point doesn't matter very much. What actually matters is our direction vector. So let's just try and find the direction vector of each of those lines. So this first line, we could choose 2 points. I'll show you a better way, but for now, let's say that we want to choose 2 points. So let's pick x equals 0 and y equals 0, just because it's simple, right? So x equals 0, when x is 0, y will be 5. So I can say for sure that the point 0, 5 is in that line. If I take y to be 0, my x, now if y is 0, my x would be 5 halves. So 5 over 2. So the point 5 over 2 and 0 is in that line as well. Now that I know 2 points of my line, I can find the direction vector. So if we take a vector going from this first point, let's call it, I don't know, A and this B, right? So if we take a vector going from point A to B, what would be this vector? So vector AB, which is our direction vector, I'll call it B1, just because this is our first line. B2, I'm going to call B2 for the second line. So what would be our vector here? So AB is x coordinate of B minus x coordinate of A. So x coordinate of B minus x coordinate of A, so that's 5 halves. And my y coordinate would be y coordinate of B minus y coordinate of A, so that's minus 5. Now, this is, let's say that this is AB. This is not our direction vector. Well, from what we have studied so far, we should notice that it doesn't actually matter if we have this exact vector or if we have any larger vector than that one. As long as it's pointing towards the same direction, right, the magnitude of this vector doesn't matter, because we can just get a different parameter and multiply it by a different number. So that t that we have in our equation that shows up here, well, we can choose that t, that parameter, or s, or any parameter that we have, to be half of what was before or twice. So our direction vector, if we get any vector which is a product or a division by a certain integer number here, we will still have a vector which is parallel to that one. So if they are parallel, they are pointing towards the same direction, so any of them can be used as your direction vector. So we can actually get a direction vector which is slightly different than that one. For example, if I multiply here by 2 on top and below, so we would have a vector which is 5 and negative 10, right? This would be another vector, let's call it, I don't know, C. Right, so this vector C, I've just multiplied by 2, so it's 2AB. It's a vector which is parallel to AB, so it is our direction vector as well. We would just have a different parameter. If this was, let's say, multiplied by a parameter P, and this was multiplied by a parameter S, any parameter T that I take here will be twice as large as our parameters S. If I have S equals 1, T will have to be 2 here, so we have exactly the same value, exactly the same point. If we take the same arbitrary point of our line, then we would need to take S to be exactly half of T. Anyway, so this is also a vector which is a direction vector to that line, but there is a much simpler one. We can simplify on top and below by 5. So we would have a vector which magnitude would be much smaller, however it's still the same direction. So this could be our direction vector. This is our direction vector for our first line here. What I discussed before, what I told you that there is an easy way to do this, well, you can actually take a look at the gradient of your line, and if you take, let's say that your gradient is, well, let's say that it's just, I don't know, B over A. I didn't want to use the same letters. Alright, so if your gradient is B over A, your direction vector, I'll call it V here, it will be A, B. As simple as that. So let's check with this line here. So this line, if I rearrange to make y my subject, I would have 5 minus 2x. So indeed my gradient is negative 2. So gradient is negative 2 over 1. That would be my gradient. So if I flip those, I would have 1 over and negative 2, which is exactly what I have here, 1 and negative 2. So for the second line, let's follow this much simpler procedure. So let's try and get 2i to be the subject first. So 2i will be 8, will be minus 8 plus 3x, right? And well, y, then we divide everything by 2, so negative 4. I could have the 3 halves of x first, minus 4. So where's our gradient? Well, it's here. So since our gradient is 3 over 2, our direction vector, for this one I will call b2, would be, all of them are positive, so it's 2, 3. If you wanted to do it, you can do exactly the same thing. You assume this to be 0, you have 3x equals 8. You assume this to be 0, you have negative y equals 8. And then you can simplify, you can get the simplest or a better vector. This would be it. Alright, so 2 and 3 is our direction vector. So all we have to do now is use what we know. So basically it's the cosine rule again, slightly different. So it's the dot product now. So absolute value, well, b1, b2 over magnitude of direction vector b1 multiplied by magnitude of direction vector b2. So b1 dot product with b2. So absolute value. Now b1, so x1 times x2. So 1 and 2, 1 times 2, plus negative 2 times 3. Now all of this is absolute value, so it's going to turn into a positive number, even though I can see that it would be negative, but it's going to turn into a positive number. Now magnitudes, let's work them here. So b1 would be root of 1 squared plus negative 2 squared. I'm just putting all of it here so you know where those numbers come from, because sometimes you guys get lost. So 1 squared plus negative 2 squared, that's root of 5. What about b2? Well, b2 root, we have 2 and 3, so that's 2 squared plus 3 squared. So 2 squared is 4, 3 squared is 9, so this is root of 13. So we're going to have here root of 5 times root of 13. So our cosine of theta, which is the cosine of the angle between those two lines, between those two vectors, hence between those two lines, would be then 4, because here 1 times 2, that's 2, negative 2 times 3, that's negative 6, negative 6 plus 2, that's negative 4, but absolute value of negative 4, it's 4, over those 2/3, right? If you're allowed a calculator, just leave them here, because now what you're going to do, you're going to have your theta will be the arc cosine, or the inverse cosine if you prefer, of 4 over root of 5 root of 13. And then if you put that in your calculator and you solve it, you should have a value of approximately 60.3 degrees, approximately. Alright, and there you go. So now you should be able to find the angle between any two lines, 2 dimension or 3 dimensions.